Hello, all. Welcome back to Virtual AP Stat. I am your host, Mr. Walsh. We are finishing up Chapter 11 today. Before I get into Chapter 11, I want to make just a couple of announcements. You have seen recently that Princeton Public Schools put out an email saying that we will be at remote learning and remote teaching until at least April 17th. So unfortunately, I won't be seeing you guys anytime soon. But we will be prepping for the AP exam virtually, essentially, because the AP exam is being changed. It is going to be a 45-minute exam taken at home on your home device, either your laptop, iPad, or even your phone. And they're going to put out, College Board will put out an announcement between now and April 3rd to kind of finalize how the exam will look and what will be on the exam. So my guess is that chapter 12 will not be on the exam. So when they make that announcement, we will then change our curriculum. But as of right now, we're going to finish out chapter 11, which is our last chi-squared test. And then we'll just maybe start preparing for an online AP exam, depending on what their announcement is. So keep an eye out on your emails and keep an eye out on our websites for announcements on the upcoming AP exam and its changes. So today's video will be pretty short. It is just the last chi-squared test. It's called chi-squared test for association or independence. You'll see it as both. So again, chi-squared test for association or independence. The very first chi-squared test we did was a chi-squared test for goodness of fit, and it looked at one population and one variable. So again, our first example was the color distribution in M&Ms. Our variable was color, our population was M&Ms. In our second chi-squared test, we call it the chi-squared test for homogeneity. It was two or more populations and one variable. So our example we did was the variable was the entree chosen, and the population was the different types of music playing in the background. Our last chi-squared test is called the chi-squared test for independence or association, and that is a single population but multiple variables. Okay, it's going to look exactly the same as a chi-squared test for homogeneity. The only difference is your hypothesis and your conclusion. Okay, so our conditions are going to be the same. We're going to have random, 10%, and large counts. Our large counts is that our expected values are greater than 5. Again, if you're referring to expected values, you need to write the expected values down. Your calculator can do it for you. Okay, I showed you last week, I guess, how your calculator can do it for you. So use the power of the calculator. If you don't want to use the calculator, you can do the row total times the column total over the table total, and that will give you the expected value of each cell in your two-way table. The hypotheses, like I said, is the only thing that's different. When we're doing a chi-squared test for independence or a chi-squared test for association, same thing. Our null hypothesis is that there is no association between the two variables, because now we're looking at two variables in one population. Okay, and we're looking to see if there's an association between the two variables. Whereas before, we had one variable in two populations or three populations. Now it's one population, multiple variables. Our alternative hypothesis is that there is an association between the two variables. Okay, so again, the null hypothesis is that there is no association. The alternative is that there is an association. That chi-squared value is calculated the exact same way. You find the chi-squared contributor for each cell, and then you add them all together. That's why it's the sum of the observed minus the expected squared. divided by the expected. Of course, you can let your calculator find that chi-squared value for you. Your degrees of freedom, calculated the exact same way. It's the number of rows minus 1 times the number of columns minus 1. And then if you find your p-value to be statistically significant, you can go ahead and do a follow-up analysis to see what cell is contributing the most to your chi-squared value. Okay, so the example we're going to do today, this is, are men and women equally likely to suffer lingering fear from watching scary movies as children? Researchers asked a random sample of 117 college students to write narrative accounts of their exposure to scary movies before the age of 13. For more than 1/4 of the students said that some of the fright symptoms are still present when they are awake. The following table breaks down the results by gender. So this looks the exact same as a chi-square test for homogeneity. The only difference between a chi-square test for homogeneity and a chi-square test for independence is the way the sample is taken. Okay? So because a chi-square test for homogeneity is multiple populations, you're going to take multiple samples or have multiple treatments. In this example, I have one random sample. It says researchers asked a single random sample of 117 college students, which means that this is not multiple populations. This is one population, and the population is college students. Okay, that's why this is not a chi-squared test for homogeneity. This is a chi-squared test for independence. It is a single sample, a single population. There are two variables. The first variable is gender, male, female. The second variable is, do they have fright symptoms, yes or no? That's what makes this a two-way table, is that my rows and columns both represent variables, not populations. There is one population. The population is college students. So our first question, so I do the chi-square test for you. Sometimes they'll give you this and ask you to interpret things. Sometimes they won't. The chi-square test is the exact same chi-square test in your calculator. So homogeneity and independence, the actual test in the calculator is the same, but the name of the test is different. Okay. So again, here is my chi-square, my Minitab output for my data. You can see that males with fright symptoms looks like the chi-squared contributor is very large, whereas females with no fright symptoms looks like the contributor is very small right here at a 0.403. My degrees of freedom is 1 because I have a 2 by 2 matrix. So 2 minus 1 times 2 minus 1 is 1. I got a p-value of 0.045, which is small, but depending on my alpha level, will change if I reject or fail to reject. So this is my Minitab output. I have my observed counts, my expected counts, and my chi-squared contributor for each cell. Now, if I added these cells up, I would get my chi-squared value, which is right here. Okay. The first question is, explain why a chi-square test for independence and not a chi-square test for homogeneity is good for this setting. This is exactly what I just explained. This is a single random sample of college kids. Once I got the sample, I then classified them by gender, variable number 1, and whether or not they had lingering fright symptoms, variable number 2. So 2 variables, 1 population. The only way I can make this into a chi-squared test for homogeneity was if I took if I took 2 random samples. If I took a sample of males and then a sample of females, now I have 2 populations, male and females. But because I took 1 single random sample of college students, I had 1 population, and that's why it's a chi-squared test for independence. That's the only difference between these 2 tests, is the way the samples are taken. Okay, the hypothesis, that's the other thing that's different between these 2 tests. So I have my null hypothesis is that there is no association between gender and ongoing fright symptoms in the population of college students. While the alternative is that there is an association between gender and ongoing fright symptoms. So the two tests, chi-square test for independence and chi-square test for homogeneity, just answer different questions. The samples are taken differently, and then their hypotheses are taken differently. So therefore, their conclusions will be a little different. But the actual tests themselves will be the same. The way you do them in the calculator, at least. Okay. Looking again at my Minitab output, the question says which cell contributes the most to a chi-squared statistic. And I told you we looked at that before, and it looks like male with fright symptoms is the biggest contributor. They expected 7, and they expected 11.69. They only observed 7, and they got a contributor of 1.883. So there was a lot fewer males than were expected. Okay. And then, of course, our last thing, the p-value, 0.045. Now, they're going to give us an alpha of 0.01. That's important, because if they gave us an alpha of 0.05, we would have rejected. But because we have an alpha of 0.01, we are going to end up failing to reject. We do not have convincing evidence that there is an association between gender and fright symptoms in this population of college students. Okay. So again, we have 3 chi-squared tests. We have a chi-squared test for goodness of fit. That one's easy to spot. It's one population, one variable. Usually the data is in a list. The other 2 chi-squared tests look almost identical, the homogeneity and then the independence. The only difference is the way the samples are taken. Homogeneity is multiple populations, so you'll have multiple samples. Independence is one population, so you're going to have one random sample. The actual calculation of the test itself is the same for homogeneity and independence. The null hypothesis and the conclusion is different. So a chi-square test for independence, we're looking at an association between 2 variables. A chi-square test for homogeneity, we're looking at the distribution of a categorical variable across multiple populations. Okay? That's all I have for you guys today. We will hopefully start our AP review in our next video. Thanks.